In this screencast, we're talking about acid-base neutralization reactions, our second sort of grouping of aqueous phase reactions after precipitation reactions. So the first thing we need to do is sort of talk about acids and what they represent. So we know that HBr, hydrogen bromide, hydrobromic acid, is a strong electrolyte. We have some sort of indication that hydrobromic acid is a strong electrolyte because it is a bromide-containing species. And if you remember back to our solubility rules, all bromides, with the exception of silver, lead, and mercury, all bromides are strong electrolytes. And sure enough, hydrogen bromide, hydrobromic acid, is a strong electrolyte, which means it completely dissociates in solution. So again, here we sort of have when we write HBr sub AQ, that's supposed to be AQ. I know it doesn't look like one, but it is. Trust me. When we write HBr sub AQ, that's an equal sign, not an arrow. What we really mean is we have one H plus and one Br minus. We made the same sort of discussion when we were talking about sodium chloride. When we write NaCl sub aqueous, we know, because we're smart general chemistry students, that that really means that it actually is dissociated. So it's sort of a shorthand notation for it. The fact that hydrogen ion appears in solution is the definition of an acid. There's multiple definitions of acid, but the most basic is anything that forms aqueous hydrogen ion. So hydrobromic acid, hydrochloric acid, sulfuric acid, all of those acids that you're sort of familiar with, they all dissociate in water to form hydrogen ion. So if we were to ask, if we write 2.4 molar HBr, that is the equivalent to saying that the hydrogen ion is 2.4 molar. The bromine ion is 2.4 molar because for every 1 mole of HBr that dissociates, I get 1 mole of hydrogen ion and 1 mole of bromide ion. And we might actually write HBr is equal to 2.4 molar. The concentration of HBr, all I'm saying here is the concentration of HBr of the actual molecule together is technically 0.0 because this doesn't exist, because it's a strong electrolyte. But we will write it like and say, okay, HBr, the concentration, and we have a little square braces representing concentration, is 2.4 molar. What that really means, in truth, is that the hydrogen ion is 2.4 molar. Now, depending on who you ask, depending on what textbook you look at, you'll find different lists of what are known as strong acids. So the 7 acids that I say are strong acids, strong electrolytes, they completely dissociate, are hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, and those should all be pretty much no-brainers. Those first 5 should be no-brainers because HCl, Br, and I are on our solubility list of anything that's tied with one of those anions is, a strong electrolyte. Here these acids are. They're strong electrolytes. There's nitric acid, all nitrates soluble. There's sulfuric acid, all sulfates are soluble. Then we have 2 others, perchloric and chloric acid, HCl3 and HCl4. So those are our strong acids. Now, if there's only 7 strong acids, that means that all the other acids in the world are weak acids. If you're a weak acid, then you are a weak electrolyte. What does that really mean? Well, I'm going to introduce a new sort of picture to you, and that is this double-headed sort of reaction arrow. And you'll notice there's two heads to it. One is sort of, the bigger one is pointing towards this is acetic acid. The smaller one is pointing toward the acetate ion and the hydrogen ion. So a weak electrolyte, if you recall, a weak electrolyte is one that is defined as a substance where only few ions exist. It doesn't completely dissociate. This is a dissociation. Acetic acid falling apart into acetate ion and hydrogen ion. It's a dissociation, but we don't have a complete dissociation like we do in these strong acids. In a weak electrolyte, it only partially dissociates. So what that means is, if I write this acetic acid and write this little AQ, what that means is that most of the acetic acid still stays together as a molecule. But some of them, think of it maybe 10, 15, 20%, just for example, for a number, 10 or 15% of those at any one particular point in time actually fall apart into an acetate ion and a hydrogen ion. Most of them are still together. Some actually dissociate and form anions. And when we start talking about later in future courses about strengths of acids, it's really a function of how much does this reaction sort of flood to the right. So the more hydrogen ion we make, the stronger the acid is. These 7 acids are all strong because they completely dissociate. They all go all the way to the right-hand side of the equivalent reaction, if you will. They all dissociate, so they all form H plus in solution. They completely dissociate. The weaker acids, only some of them dissociate. So that's why we call them weak acids, because they're weak electrolytes. Now, bases, on the other hand, their definition are species that form hydroxide ion in solution. Sodium hydroxide is a perfect example of a very simple and strong base. It's a base, there's our sodium ion, and we know that all sodium salts are soluble. So if we take sodium hydroxide, it dissociates into sodium and hydroxide. That's why we call this sodium hydroxide. Surprise, surprise. And it completely dissociates. Again, there's that equal sign. So if I write NaOH, AQ, since I know, because I'm a smart chemistry student, that sodium hydroxide is a strong electrolyte, it's a strong base, it means it completely dissociates. I write it like this, but in truth and in reality, it's this and this. So most bases are weak, just like most acids are weak. Here is an example of a weak base. This weak base is ammonia. Now, in sodium hydroxide, it was sort of obvious that it was a base in solution because there's the hydroxide ion. It just falls apart. There's the OH. You can be a base and not have any OH around you. So this is ammonia, NH3. It's got no OHs on it at all. The little AQ means it's dissolved in water. And so what's going to happen is one of those zillions of water molecules that surrounds the ammonia, one of them, we're going to call it this one, reacts, and the ammonia takes one of the hydrogen ions and forms the ammonium +1 ion, which you recognize. And what's left after the water has been robbed of its hydrogen ion is a hydroxide ion. So that little OH there means that ammonia is a base, because when I put ammonia in water, hydroxide ion popped out. That's the definition of a base. The hydroxide doesn't have to come from what you are, just that hydroxide ion has to sort of appear after you add water. And again, as you can see, we have this double-headed arrow, so ammonia is actually a weak base, and so most of the ammonia is over there, and some of it dissociates, or actually in this case reacts with the water, to form ammonium ion and hydroxide ion. So just like with our strong acids, we have a list of strong bases. Those are the group 1A hydroxides, so sodium hydroxide, lithium hydroxide, potassium hydroxide. Those are all strong bases, in addition to calcium hydroxide, strontium hydroxide, and barium hydroxide. These are the other 3 strong bases. You might want to look on your periodic table and note their location. Calcium, strontium, and barium are all right next to each other, below magnesium and beryllium. So now we can talk about those. We can finally talk about those second kinds of reactions. Those are what are called neutralization reactions, and they all have sort of the same general layout. That it's an acid plus a base gives a neutral species and water. What I mean by neutral species is, something that's not acidic nor basic, really. So let us consider a very simple neutralization reaction. Here we have hydrochloric acid, a strong acid, reacting with sodium hydroxide, a strong base. And if we just sort of follow the same rules that we did before, in terms of the precipitation reaction, swapping partners and predicting products, we take the cation from the sodium hydroxide to the sodium and mix it with the chloride ion. We know that that's a soluble compound, so I write sub AQ. And I take the H plus and I take the OH minus, acid plus base, and those combine to form water liquid. Now notice this is water liquid, not water sub AQ. Water with a little AQ behind it doesn't make any sense. You can have water dissolved in water. That just doesn't make any sense. It actually comes together and forms the molecule water. So if you will, we know, so if we write this as the complete ionic equation, break up the hydrogen and the chlorine, the sodium and the hydroxide, there's our water, and we still have sodium ion and chloride ion, and we follow our rules of removing spectators. We know that sodium and chlorine are spectators, because they got one sodium, one chlorine, and we are left with the net ionic equation of hydrogen ion reacting with hydroxide ion to form one water liquid. That's our net ionic equation. Notice that the identity of sort of the acid and the identity of the base, nobody really cares. So if I did nitric acid and sodium hydroxide, it'd be the same. Because then if this was, HNO3 instead of HCl and sodium hydroxide, my product would be sodium nitrate. You know what? That's soluble too. So in that case, the sodium and the nitrate would be spectators, and that would have the same net ionic equation. Most neutralization reactions have this as their net ionic equation. Most of them. Not all, but most. Here's another simple one. Magnesium hydroxide, which is not a strong base, but it's certainly a base. This is actually the active ingredient in the antacid product Mylanta. Reacts with hydrochloric acid, that would be your stomach acid, makes magnesium chloride, which we know is soluble, and our water liquid. Magnesium hydroxide, we sort of write that out in terms of the reaction. We separate them. So we have a magnesium plus 2 ion, 2 hydroxide ions, separate the hydrochloric acid into hydrogen ion and chloride ion. Of course, we've already balanced this, giving us 2 waters. We needed to have a 2 in front of that HCl before we got to this. So here everything in blue is our complete ionic equation. Everything that exists as ion is written as ion. Then we remove the spectators. In this case, magnesium ion and chloride ion are spectators, leaving us with a net ionic equation of, well, that's the same thing as we had before. Hydrogen ion plus hydroxide ion gives water. Now, don't let the 2, 2, and 2 fool you, because remember, these are balanced chemical equations, and so we can multiply them all by the same stoichiometric coefficient. It doesn't change anything of consequence. So there's 2 examples, simple neutralization reactions that have the same net ionic equation. You need to be able to, in my course, need to be able to recognize them and write these complete ionic and net ionic equations. I do just want to show you one example of a neutralization reaction where something else happens. I'm not expecting you to memorize this. I just want to sort of show you, hey, look, something else can happen in a neutralization reaction. This is the reaction between hydrochloric acid and baking soda. Baking soda is sort of it's a very cool, awesome chemical that's been used for centuries for all sorts of things. It's a really good cleaning agent. One of the things that most people don't know you can do with it is you can use it as an antacid. You can take a very small amount of it, don't take too much, just a small amount of it, mix it with water, and I'll tell you right now that it tastes horrible. Swallow that baking soda, it will react with the excess hydrochloric acid in your stomach. That's why you have an upset stomach. And what you make is sodium chloride solution. That's fine. There's your water. That's a neutralization reaction. But the other product that you get is carbon dioxide gas. Yes, you drink that 8 ounces of baking soda laced water, and of course you're drinking it quickly because it tastes horrible. And what happens is you very quickly burp very loud. Yes, I say that from experience. Happened to me one time when I had really bad acid indigestion and I needed something to react, and I looked on the side of my baking soda box and there was the recipe telling me how much to make, and it tasted horrible, so I sort of slammed my 8-ounce glass of water down and then let out the loudest burp I've ever given off in my entire life. So our net ionic equation, you go through and remove everything. Here's sort of our net ionic equation. There's a hydrogen ion, the bicarbonate, the HCO3, that's what that's actually called. This is actually acting as a base. It's a base in and of itself, just trust me. And they neutralize each other and form water and carbon dioxide. Good luck.